topic of this lecture, and this is 7.2 of the Griffith Introduction to Electrodynamics, and this is electromagnetic induction, and the second, the 7.21, is the Faraday's law. So what is Faraday's law? We should know about in detail. In 1831, this is very early, in 1831, Michael Faraday reported a series of experiments. They have done three types of experiments, and they observed that they have the same result, the EMF that they have reported. So the first experiment, this is the magnetic field. This is actually the magnetic field, and this is a loop of coil. And in the first experiment, they move the coil with velocity v in this direction, and they have reported the EMF. And the EMF that they have reported as that EMF can be generated. In the other experiment, this is the magnetic field, and here the coil remains constant. The velocity of this coil is equal to 0, and they move the magnetic field, which is in this opposite direction, this left direction, and still they have generated and they have reported the EMF. And the third one, they have remains constant the loop, the magnetic field. They are not in motion, but they are still in static position, but they have changed the strength of magnetic field that they have provided, and they observed the same EMF. So they have the same EMF in this and this, but I think in these 1 and 2 experiment, in these times, I think they don't know about the theory of relativity, because when this is a static, this is moving, and this is moving, they don't know about the relativity at that time. So actually they have the same results. And in the third one, both the magnetic field and this are the velocities are 0, and they have only changed the strength of the magnetic field. And the two first experiment, in experiment 1 and experiment 2, it is straightforward case of motional EMF. These two, these are motional EMF. This can be generated due to the motional EMF, and one can get minus d phi divided by dt. Here the flux change, and one can get the EMF. But from third experiment, a changing magnetic field induces an electric field. How this is no motional EMF, but when the strength of the magnetic field is changing, then a changing magnetic field induces an electric field here. So a changing here from the third experiment, a changing magnetic field induces an electric field. So this is important. and one may write down like this EMF, this can be generated due to the changing in magnetic electric field minus d phi divided by dt. Then it means that this is equal to minus d phi divided by dt. And if we put the value of phi in integral form, then this must be equal to d dot dl minus d divided by dt integral of b dot dA. This is flux must be equal to b dot dA. And whenever we apply this time derivative, then we can get dp divided by dt dot dA. Now this is the integral form. This is the integral form of Faraday's law. Now using a Stokes theorem, applying the Stokes theorem to the left side of this equation, we can get the differential form of the Faraday's law. So what is Stokes theorem? We know about the Stokes theorem. So using the Stokes theorem, then we can use for the left side only. So E dot dl, this must be equal to the curl of E dot dA. This is actually the Stokes theorem. And using this in equation this, then putting the left hand side here, so from equation this we can get del cross E dot dA, which is equal to minus dp divided by dt dot dA. So from this we can remove this integration, this and this, and we can get only del cross E, which is equal to minus partial b divided by partial t, and differential form in the partial derivative we can write down. So this is the differential form. This is the differential form of Faraday's law. Okay. You can note this, and I want to erase this. Now, in electrostatics, we studied that del cross E, which is equal to 0 when charges are at rest. Already we know about this. When charge is in a state of rest, then we can find out the curl of E must be equal to 0. But from Faraday's law, del cross E, which is equal to minus partial B divided by partial T, how we can get the curl of E is equal to 0 and using a Faraday's law? It is possible when the magnetic field is constant. If the magnetic field is constant, then the rate of change of time, this will goes to 0. If this is constant, if B is constant, then del cross E, which is equal to 0. From electrostatics, when the charge is at rest, from magnetostatics, if we, from the Faraday's law, if B is constant, then the curl of this is equal to 0. Now, a universal law. Let's discuss these experiments in detail, and one can get some different results. I write down some universal flux law. Universal flux law. This means that whenever the flux change with time, we will get EMF. We will get EMF. Now come to the experiment that the Faradays have suggested and they have proposed. In experiment 1, the force F is equal to the force in experiment 1 F is equal to Q V cross B is responsible for EMF, because when we pull the loop to the right side with velocity V, then this length, this segment will move. If this moves, the charge will also move. So this is a motional EMF. And this force, because this has some velocity with the magnetic field, so this force is responsible for the EMF. But in these two experiments, because in this experiment the magnetic field is moving in this direction, so there is no motion of this loop. In the third experiment, the loop and the magnetic field have velocity 0, only the strength of the magnetic field is changing. So who is responsible for the EMF here? Here is this force, but here the charges in the segment remains in a static position. So in experiment 2, and 3, the changing the magnetic field induces electric field. So electric field, it should be noted that this electric field that has been generated produces EMF. This point should be noted. Electric field act on the charges. Here, the electric field act on these and the charges, and EMF can be produced. So now the point I will repeat these points because this is very, very important. Here, in experiment 1, this force is responsible for the EMF. In these two experiments, the coil remains constant, so the rate of change of magnetic flux induces the electric field, and this electric field is responsible to produce EMF.